Good morning, everyone. This is Rona Palmer from Fluke Excelix. And thanks for joining us today for this installment of our Best Practice webinar series. And let me just take a moment and clarify our Best Practices webinars. And during these, we focus not on specific technologies or on software, but rather on maintenance strategies and practices. And we invite different guest speakers with a variety of backgrounds to share their experiences and their expertise. And I'm very pleased to have with us today as guest speaker, Nancy Regan, who's the founder and president of The Force, Inc. And she's going to be presenting today's topic, the powerful philosophy behind RCM. Good morning, Nancy, and hey, thank you for being with us today.
Good morning, Rona. Thank you. I'm delighted to be here.
And Nancy, while we have quite a large group today, and while they're logging in, I'm wondering, Nancy, you and I chatted earlier, and you've been in this field for over a couple of decades, and maybe you can speak to some of the trends you see or some of the changes that prompted you to want to share this particular topic with our listeners today, and why you feel it's important.
Yes, something that I see happening in our industry today is that obviously we've got a lot of technological advances, and I notice that organizations get busy with the technology and sometimes even contract what I call shiny object syndrome. And so they don't focus so much on fundamentals anymore, just basic fundamentals of maintenance and reliability. But from my perspective, the fundamentals are the foundation of our reliability program. It's just like the foundation of a building or a house. And so that is why I'm inspired to speak about what I'm going to share today, that I would not want to live without technology, and I think it plays a very important role in our industry, but I think that it needs to be implemented properly.
Excellent. All right. Well, we look forward to hearing what you're going to be sharing. But before I turn things over to Nancy, a few quick housekeeping items. We are recording today's session. We'll be sharing a link to the recording with all of our listeners today, but I have your phones on mute so we can get a nice clean recording. But Nancy has agreed to stay with us after her formal presentation to answer any of your questions. So please feel free to type your questions at any time during the presentation into the questions feature in GoToWebinar, and then we'll read them to Nancy at the conclusion of her slides. We'll also be sharing a PDF of Nancy's slides with all of our listeners today. And there'll be a survey that at the end of the presentation, and you can request a copy of the slide deck there. All right, I think that's it for housekeeping. So Nancy, I'll turn it over to you.
Okay, thank you, Rona. Okay, so one of my guilty pleasures is that I love to play No Limit Texas Hold'em poker. And I was in Tunica, Mississippi a few years ago, and I was playing in a No Limit Texas Hold'em poker tournament. And so before I knew it, there were only 30 players remaining, and then there were 20, and then there were 10, which meant that I made the final table. And then just like that, there are only 2 players left, and I was one of them. So I had been playing pretty well up to that point, but I'm going to come clean and just let you know that when it came down to just me and my opponent, I got scared and I started to play horribly. I was playing, as they say in poker, I was playing fit or fold, which meant I bet when I had a good hand and I folded when I didn't. And my opponent obviously caught on to this and he exploited my weakness. Before I knew it, he had 80% of the chips in play. Now, luckily for me, it was time for a scheduled break, and my husband took me aside and he said, You're letting him steamroll you. He said, you're just not playing well. And my stomach sunk because I knew he was right. So I went in the bathroom and I locked myself in a stall and I gave myself a good talking to. And I steeled myself and I resolved to turn it all around after this break. So as I'm still in the stall, I put my headphones in and I listened to a little bit of Vanilla Ice to kind of get me into the groove. I sit back down at the table, play resumed. I got aggressive when it was appropriate, and I threw in a few timely bluffs, and within 30 minutes, I won the tournament. Now, if I asked you rhetorically, what was my difference in play before and after the break? It was my philosophy. I mean, if you play fit or fold in poker in the long run, you're going to lose every time. But when you play smartly, you stand a chance to win. So when I was in that bathroom stall, I shifted my philosophy and I designed my choices to give myself a chance at winning that tournament. And the way I see it, the way we win at reliability is very similar. In fact, when it comes to reliability, we as equipment custodians, we design our reliability to a very large extent. In fact, we design it both literally and figuratively. The reliability that we achieve is largely dependent upon the design of our equipment, that is, its inherent reliability. In other words, what inherent reliability is it means we can't get anything more out of a piece of equipment than what it was designed to do. In other words, it is what it is. But as equipment custodians, we also figuratively design the reliability of our equipment. I mean, the definition of inherent reliability doesn't mean how long an item will last without any failures. Inherent reliability means the kind of reliability that an item exhibits when it's protected by, for example, the right maintenance, but not just maintenance, also some other what I call default strategies, things like the kind of operating procedures that we have in place and the quality of our technical publications and our training programs and our emergency procedures, and also, for example, operational tempo and environment, where we're going to use our equipment and how often we're going to use it. So all of these default strategies, or the things that we use to take care of our equipment, are all dependent upon our choices, and our choices are governed by our philosophy. If we have a poor philosophy, then we make poor choices. We get steamrolled by our opponent at the poker table. But even worse, as asset managers, we get steamrolled by our equipment and we end up with increased costs and chronic downtime and living in reactive mode, running from fire to fire and dealing with frazzled teams. But when we have an effective philosophy, then we make winning choices. In other words, we do the right maintenance at the right time, and we take care of our safety devices properly, and we fix deficiencies in our training programs and improve our operating procedures. And, that's just to name a few. So the question then is, what makes up a winning reliability philosophy? And for me, what I say is that when it comes to equipment reliability, what we need to do is begin at the beginning. Now, here's what my mentor, John Mowbray, taught me about reliability. John taught me that reliability isn't a thing on its own, but rather reliability is sprinkled amongst all of the functions of a piece of equipment. So I'm sure that there are a lot of people on this call today who are familiar with a failure modes and effects analysis, that you know what it is. And I'm sure a lot of you have actually participated in a failure modes and effects analysis. So for those of you who maybe haven't, a failure modes and effects analysis starts by identifying functions. And that's no coincidence, because this is what John taught me. When we write equipment functions, we actually define the kind of reliability that we need from our equipment. So really, when we write functions, it's like goal setting for our equipment. And we can just think about it, I like to think about it as human beings, or for my own self and my own personal and my professional life. When we have no goals, whether it's short-term goals for the day or long-term goals for 6 months or for a year, when we don't have anything established, then we take uncertain steps each day. We get busy in email and making phone calls, and things come up, and then before we know it, we're not even sure what we did at the end of the day. But when we have goals, then we take meaningful steps to achieve our objectives. So really, writing functions is like recording our vision of the future for our equipment. And if we're designing our future, then it's essential that we start with clarity about what we need. And we've got to be specific. So now what I'm going to ask you to do is indulge me for the next 60 seconds, because I want to go through an example with you, and you may be wondering why I'm spending your valuable time talking about something so simple and obvious. So don't look at your phones and don't look at your email. Let's just go through this example together. Okay, so a winning reliability philosophy starts with clarity about what is required from an asset. And I'm not talking about, I'm just waiting for the lag on the slides. I'm not talking about how the design engineers envisioned it being used, and I'm not talking about how the manufacturer planned on it being used. I'm talking about what the organization that procured it actually requires from it. So when it comes to equipment reliability, we can define performance in two different ways. Number one, by talking about design capability, and by talking about required performance. So let's just take, for example, a tow tractor, and let's say that the design capability for my tow tractor is 30,000 pounds. But what I need it to do is to tow 40,000 pounds. Well, if I were to ask you if that is acceptable, well, then obviously it is not acceptable, because, of course, the required performance exceeds the design capability of the asset. But I'm sorry, the slides got lagged here. So obviously, if I needed to tow 40,000 pounds, but it's only capable of 30, then that's just not going to work. So this is a very simple, straightforward, obvious example. Now what I want to do is I want to talk about 3 air tankers that crashed while responding to forest fires, because this whole idea about design capability versus required performance is just so painfully obvious, but it's so obvious that it's overlooked in our world. And when this gets overlooked, disaster can happen and people can actually lose their lives. And this has happened. So let's look at 3 air tanker crashes: a C-130A, 2 C-130As, and a P-4Y privateer. So the first crash happened on August 13th, 1994, where there was in-flight separation of the right wing. This happened near Pear Blossom, California, and all 3 crew members were killed and the airplane was destroyed. With the second C-130 crash, it was again in-flight separation of the right wing. Everyone on board died and the airplane was destroyed. And with the P-4Y privateer, there was in-flight separation of the left wing. And on that crash, both crew died and the airplane was destroyed. Now, the common thread amongst these 3 crashes is that all 3 aircraft were leased by the United States Department of Agriculture's Forest Service for public firefighting flights. But the aircraft were originally designed to transport cargo for the US military, not to fight forest fires, but they were retrofitted to do so. So if we go back to what we talked about before, where there are all kinds of things that affect the reliability of our equipment, not just the kind of maintenance that we do on it, but all these other elements, including operational tempo and the environment. So in this case, we're fighting, their goal was to fight forest fires. Now, the operating environment and the loads experienced by an aircraft transporting cargo are vastly different from those experienced by an aircraft fighting forest fires. Now, what we learned from the NTSB safety recommendation is it explained this, that during a firefighting mission, an aircraft experiences frequent and aggressive low-level maneuvers with high acceleration loads and high levels of atmospheric turbulence. I'm just waiting for the lag. Okay. Just waiting for the lag to catch up. Sorry. Okay, the report detailed that the structural lives of the aircraft were shortened because of the harsh operating environment and the far more aggressive loads applied to the aircraft during firefighting versus transporting cargo. The report further detailed that the maintenance programs used for the aircraft were the same that were derived for the aircraft when their mission was transporting cargo for the military. The report concluded that the aircraft were likely operating outside the manufacturer's original design intent. So in this example, with these 3 aircraft crashes, the required performance, that is firefighting, exceeded the design capability of transporting cargo. So this simple idea of required performance versus design capability was completely overlooked. So what I want to do is pause for just a moment, and I want to talk about why I'm bringing up these 3 crashes. You know, it's easy for us as human beings to look back on any disasters and point fingers and, show why people were wrong with the decisions that they made. But that's not my intention with this. The reason that I'm bringing these 3 aircraft crashes up is to point out the fact that oftentimes the basics, the fundamentals, the simple things in our world or in our industry are often overlooked, and sometimes that can lead to disaster. So when we have a firm foundation, we can very positively affect the reliability of our equipment. So if they had gone back and considered functions or written the functions for what they wanted for firefighting versus transporting cargo, maybe it could have made a difference. But even if an organization takes the time to write functions, it's often done as a matter of routine and they lack the required details. So this is what I want to talk about. I want to talk about functions for a moment and how they relate in a failure modes and effects analysis. So I want to show you some real world examples. On the left-hand side of the screen, I want to show you functions from an air compressor analysis that yielded poor results. And I was asked to review this analysis and give my opinion on it and why I thought they didn't get the results that they were looking for. And on the right-hand side, I'm going to show you some examples from an air compressor analysis that I facilitated. So they were different compressors, they were different analyses, but I want to show you the difference in the functions. So these are real-world examples. The first one on the left-hand side is deliver compressed air to the tank. So when you have a look at this function, this pretty much describes just about every air compressor on the planet. Another function is filter and remove particulates from the intake air. Well, that pretty much describes just about every intake air filter. And another function is monitor pressure level. So again, another generic function. It doesn't really describe exactly what we need these items to do. So now let's take a look at more detailed functions describing exactly what we need this compressor to do. So how about this for a primary function? To provide compressed air that is oil-free at less than 95 degrees Fahrenheit at a minimum of 3,500 standard cubic feet per minute, 100 psig output pressure with a minimum of 5 psig rise to surge to make up this compressor's portion of maintaining 11,000 standard cubic feet per minute and 90 psig head of pressure to the plant. So obviously you can look at the first two functions and you can compare them, where the one on the left-hand side is quite generic, but the one on the right-hand side is very detailed. So in other words, we have described exactly what we need. So in essence, we have described the kind of reliability that we're looking for out of that compressor. Let's look at the next one. To remove particles greater than or equal to 1 micron from the incoming air to the compressor. So again, we've been more specific. We've described exactly how well we need this filter to filter. And then to indicate main oil discharge pressure within plus or minus 3 psi. So we've been very specific about what we need this indicator to do. So you can see that on the left-hand side, we've basically written functions as a matter of routine, but on the right-hand side, we have defined the kind of reliability that we need and want from our equipment. So the moral of this story, so to speak, is that as equipment custodians, we have a much greater hand in the reliability of our equipment than I think we often think, and it starts by being very clear about what we need from our equipment. So it's a very basic exercise, but so basic that it's often overlooked. So I'd like to pause for a second, and I would like for us to take a poll. And so the question is, does your organization have a process to consider required performance for your assets? Either yes, no, or, well, no formal process, but it's sometimes still considered. And if you'd like to add something specific, you could put that into the questions section, and we can talk about it more at the end of the presentation. So Rona, would you start the poll?
Sure. All right, the polls are open, and Nancy is asking all of our listeners to weigh in on this question. Does your organization have a process for considering required performance of your assets? And that was a great example, Nancy, of the difference between routine and detail. All right, it looks like we have 3/4 of the votes in. We'll leave it open a few more seconds. Okay, let's go through and share results. So Nancy, it looks like 29% said yes, they do have a process. 23% say no, but 48%, nearly half, say, well, there isn't a formal process, but it's sometimes considered. All right, back to you, Nancy.
Okay, great. Yeah, I'm excited to see those. I'm excited to see those results. Okay, so now let's keep moving on and let's talk more about what makes a winning reliability philosophy. So something else that my mentor, John Mowbray, taught me is that we manage physical assets at the failure mode level. Now, when I use the word failure mode, I use it synonymously with the term failure cause. So what specifically causes a functional failure. That's what I mean when I say failure mode. So just like there's no coincidence that a FMEA starts by writing functions, but a failure modes and effects analysis also includes a step of identifying failure modes, or in other words, what would cause us not to be able to achieve those functions that we have identified. Well, the way I like to think about a failure mode is, number one, failure modes have to be written at the right level, and they have to be written with the right amount of specificity for them to be of any use to us. I like to think about a failure mode like a road. So a properly written failure mode gets us on the right road and sends us in the right direction. And that direction might be, our destination could be any number of things. In the example that I have on the screen now, maybe our goal is proactive maintenance and default strategies. Maybe you have a goal to create a new troubleshooting guide for your equipment. So the goal of our analysis dictates how detailed and how many failure modes we put in our analysis. So for purposes of this example, let's assume that we want to make a proactive maintenance routine and some default strategies. So in other words, we're going to talk about what failure modes lead us to doing is identifying the steps that we must take to achieve our objectives. So if we go back, I want to go back to the air compressor examples. So again, on the left-hand side, here's where failure modes were written as a matter of routine. And on the right, here's where failure modes were written at the right level and amount and in the right amount of detail to be effective. And just again, to remind you, these are real world examples that I'm showing you. Okay, so let's start with the left-hand side. And we had the function deliver compressed air to the tank. And two of the failure modes included in that analysis were intake filter clogged and intake filter damaged. I'm okay with intake filter clogged. I'd like to add maybe due to normal use to it. But intake filter damaged kind of leaves us hanging a little bit because we don't know what specifically caused it to be damaged. So it's difficult for us to figure out how we want to manage that. So let's take a look on the right-hand side, and let's start with the first one. Like I mentioned, if we write the failure mode, I'm just waiting for the lag to catch up. Okay, so if we write the failure mode intake filter clogged due to normal use, well, that could lead us to maybe monitoring differential pressure and replacing the filter as required. Another failure mode is intake filter deteriorates due to normal use. And maybe that might lead us to replacing the filter on a scheduled basis. And in this case, we elaborated on damaged, and we said intake filter damaged due to improper installation. So maybe that might lead us to instituting a training procedure or augmenting maintenance instructions. So you can see how the way that we write our failure modes and the level of detail that we go into very significantly impacts or dictates the solutions that we get to on the other end. Let's look at a few more examples. And let's take another failure mode for our primary function, which in this analysis on the left-hand side is valve failure. And let's look on the right-hand side. If we elaborate on that and we pressed our working group or asked the right people about what specifically causes that valve to fail, we might come up with something like intake air valve controller drifts out of adjustment due to normal use. So you see, I can work with this one on the right. On the left-hand side, it's a little too generic, and I'm not quite sure what to do with that. But with the one on the right, it might lead me, for example, to calibrate the valve at a specified interval. Let's look at a few more examples. And let's say, here's one. AC motor seizes due to excessive vibration, overheating, and electrical failure. So this is a common failure mode that you might see in some, whether it's a failure modes and effects analysis or a reliability centered maintenance analysis, or it could be it could be another improvement initiative. But oftentimes you get a bunch of failure modes and maybe even some failure effects all squeezed into one. Because really AC motor seizes due to excessive vibration. I would ask, well, what causes that vibration? And then obviously overheating, that is a failure effect of something else as well. So let's look at that broken down. So if we ask the question, well, what specifically causes that? Maybe we might come upon, for example, electric motor bearing oil deteriorates due to normal use. And that may lead me to, again, I'm just waiting for the lag. Okay, that might lead me to replace the oil on a regular basis. With this one, electric motor intake screen clogs due to normal use. That may cause me to clean the screen on a scheduled basis or monitor the differential pressure and clean it as required. With motor bearing seal leaks due to normal use, maybe I might want to monitor for leaks on rounds. And for electric motor bearings where due to normal use, maybe I might want to perform some vibration analysis. So you can see that how when they're broken down more specifically and in more detail, it allows us as equipment custodians to arrive at logical decisions instead of kind of being over here on the left-hand side, twisting in the wind, trying to figure out what's causing excessive vibration and overheating. Okay, let's move on to another thought about a winning reliability philosophy. And, you know, when it comes to an analysis like a failure modes and effects analysis, you know, an analysis like this that feeds into, for example, an RCM analysis, we end up with some default strategies, in other words, and proactive maintenance, in other words, our choices. But to get to that, all of that requires a lot of information. So the question then remains is, you know, where do we get all of that information? Where do we find the information required to formulate these strategies? So before we talk about the answer, I want to talk about another aircraft crash. So gratefully, I'm not getting on a plane for about another month. But anyway, let's talk about the crash of American Airlines Flight 191. This is actually the worst aircraft disaster in United States history in terms of the number of people who were killed. This happened on May 25th, 1979 at Chicago O'Hare. This plane was taking off from Chicago O'Hare and it was on its way to Los Angeles. So for this aircraft crash, the trouble started when American Airlines modified a maintenance task that was written by McDonnell Douglas. And this particular task called for the engine and the pylon assembly to be removed separately. But in order to save thousands of maintenance man hours, American Airlines revised the task so that the engine and the pylon were removed as one assembly. And their task called for it to be removed using a fork truck, which you can see here on the left-hand side with this, on the left-hand side photo. You can see here the fork truck and how it is supporting the engine and the pylon assembly. So the fork truck was supporting both of them while the attaching hardware was removed. But Murphy's Law came into play, as it often does with disasters, and there was a shift change partway through the task. Now, they didn't know it, but there was a failure with the forklift's hydraulic system, and it caused the assembly to tilt. And that caused deformation where the mating clevis and the engine pylon came together, where you can see in the picture on the right-hand side. Now, that caused a crack to form, but the crack wasn't visible to them. So the task was completed and the airplane was put back into service. And a couple of weeks later, the crack reached critical length, and it caused, I'm just waiting for the lag to come up. Okay, and it caused the engine to rip off the wing during takeoff. So the engine actually ripped off of the wing, flipped over the wing, and onto the ground. Now, in the cockpit, the pilots knew that they lost an engine, but they didn't know that it actually ripped away from the airplane. And when it did, as you can see here in this bottom left-hand photo, it took out several feet of the leading edge of the wing, but it also took out parts of both fully redundant hydraulic systems. So now hydraulic fluid starts to bleed off, but they don't know it because they're losing hydraulic power, and now the slats started to retract. Now, the slats on the wing are used on takeoff to increase the surface area of the wing to increase lift. So now they started to lose lift, and they didn't know it, but the left wing starts to stall. Now, per emergency procedures, the pilots went to V2 speed, which is best climb rate. But they didn't know it at the time, but they were flying faster than V2 speed. So when they reduced speed, they caused the wing to stall even more. But they didn't know that the wing was stalling because the stick shaker that literally shakes, letting the pilot know that the wing is starting to stall, was rendered inoperable because it was run by the generator that was run by the engine that was ripped off the airplane. And so as Murphy's Law was have it, there was no stick shaker that was installed on the co-pilot's column. So the left wing eventually lost lift. It rolled to the left and dove nose down, and the airplane crashed, and all 271 people on board died and 2 people on the ground. So there were 273 fatalities. Now, the thing about an aircraft crash in the United States is when an aircraft crash happens, a GO team is immediately dispatched. So a GO team is comprised of a whole bunch of specialists in specific areas, like operations, structures, systems, power plants, weather, air traffic control, survival factors, FAA, aircraft, and the engine manufacturer, and the list goes on. In this particular GO team, there were over 40 people. Now, when they interviewed Gregory Fife, former NTSB lead investigator, here's what he said. He said, there's a natural system of checks and balances. You get a lot of information. You have everybody looking at everybody else. They would provide information that you may not normally get if you were trying to do that investigation by yourself. Now, another person working on this crash was a journalist named Peter Greenberg. And what he said was this. He said, the airline, of course, they're part of the GO team. The engine manufacturer, they're part of the GO team. The actual airplane manufacturer, they're part of the GO team. Every subcontractor, they're part of the GO team. They allow these people to be on GO teams for an understandable reason, because they're the people who understand the mechanics, the physics, the chemistry of the individual items. They can actually be helpful in an investigation. So the reason why all of this is important and is helpful is because there are all of these different perspectives represented. So from my perspective, I'm sitting back and I'm thinking to myself, what if we put the same amount of effort and the same amount of resources into a proactive reliability analysis, no matter what that is, and enlist the help of a multidisciplinary team where you may have, just for example, the operator, the maintainer, the OEM, the electrician. And the thing that is key about this is that everyone, you know, there rarely is one person who knows everything about a piece of equipment. You know, all of these different specialists and equipment experts have their own perspective and their own experience and their own understanding. And when you bring all of that together in one room using a formal analysis process, what can come out of that is like magic. It's just incredible, the results that can come out of it. So it leads me to ask the question to myself, and even to ask you rhetorically, what is the key difference between a crash investigation and a reliability analysis? And the answer is that a crash investigation is reactive, and a reliability analysis that's used to figure out how we can improve things is generally proactive. Now, something else that Gregory Feith said, the former NTSB lead investigator, is he said this: the best way to characterize any aircraft that has an in-service use is that it's like wine. They get better with age. Why? Because we get a better understanding of the airplane. We identify the deficiencies, we correct them. So over that period of time, the plane becomes better. Now, what if we replace the words aircraft and airplane and plane with the word asset? It's the same thing. It doesn't matter if it's an airplane or a compressor or a tow tractor or an offshore oil platform. Really, the longer we have an asset in service, the more experience and expertise we gain. But a lot of that is lost because we don't ask the right people the right questions. So I'd like to pause now for another poll. And the first question I would like to ask you is, do you agree that a multidisciplinary team is valuable do you agree that a multidisciplinary team is valuable for proactive reliability improvement initiatives? Either yes, no, or sometimes. And so, Rona, will you start the poll?
Sure thing. So let's go ahead and get your responses. And again, we only share these in aggregate, so no wrong answers here. All right, leave it open a couple more seconds. Okay, let's go ahead and share results here. So Nancy, it looked like 87% agree that yes, a multidisciplinary team is valuable. 1% say no, and 12% are saying sometimes.
Okay, I love seeing that result, because obviously people agree that it is important. And I talk to a lot of different people in a lot of different organizations, and I ask why oftentimes a multidisciplinary team isn't assembled to do a proactive analysis. And I often hear things like it's too expensive, and we don't really have the time, and I totally get that. But on the other hand, I would say, wait till you get the bill for not doing it if you think it's expensive. And usually it's the people that I talk to are totally on board with it, and usually it's maybe upper management or the people who aren't directly involved in the equipment who maybe don't see the value. So it's up to us to show that value, and that's a topic of a whole other presentation, which is thrilling to talk about, but it's definitely another topic. Okay, let's do one more question. Do you think that many organizations spend more time on reactive analyses or on proactive analyses? So A, more time on proactive, B, more time on reactive, or 50-50? So Rona, would you start the poll?
Sure. Okay, the last poll today. Please let us know whether you feel more time is spent on proactive or on reactive, or if they're about the same in your experience. All right, we've got about 3/4 of the votes in. We'll leave it open a few more seconds. And thanks to everybody for participating. All right, let's go ahead and share results. So it looks like, Nancy, according to our listeners, 7% say more time is spent on proactive. 85% say more time spent on reactive, and about 8% say 50-50. Pretty telling.
It's very telling, yes. And like I mentioned, I have no doubt that pretty much everyone here today, agrees that that would be an excellent thing to do. But our job, I think, is making the case to get the time and resources allotted for us to do that. I just know from the analyses that I've facilitated, I've seen organizations transform because they've been trying to figure out the chronic causes of poor reliability. And the answers very often come to light when you get everyone talking together. Sometimes the operator will say, well, I'm operating it this way. And the engineer will say, oh, that's not the way it should be operated. And the operator says, well, that's what I was taught. So it's not any one person's fault. It's, it's just a systemic change that needs to be made. Okay, so obviously, if you know anything about me, then you know that I gave my technical heart and soul away to reliability-centered maintenance 22 years ago. And this is one of the first times, at least in the slide, that I'm using the term reliability-centered maintenance, because the process that I just described was RCM. And one of the reasons why I am so technically devoted to the process is because it is chock full of the basics and the fundamentals of maintenance and reliability. So even if you don't ever do RCM, just knowing that, oh my gosh, I need to sanity check and make sure my equipment is even capable of doing what I need it to do. And knowing that if you are going to identify some failure modes, writing them at the right level and in the right detail make a big difference. And just for your information, if you don't already know, the RCM process, steps 1 through 4, make up a FMEA, or a failure modes and effects analysis. When you add step 5 into the mix, you get a FMECA, failure modes, effects, and criticality analysis. And step 6 includes the consideration of condition-based maintenance. So really, RCM in many cases is one-stop shopping for these 3 processes. I hear a lot of people ask me, well, should I do FMEA or should I do CBM? But when you do reliability-centered maintenance, you do it all 3 of those anyway. So that's everything that I had planned to share with you. I would be, if we're not already connected on LinkedIn, I would be delighted if you would send me a connection request. It would be my honor to be connected. And if you're so inclined, I would love an email with you telling me what your biggest maintenance and reliability problem is. But other than that, Rona, we can open it up to questions if anyone has any questions.
Yes, certainly. And we've received many thus far, and keep typing them in. We'll answer as many as we can during the live presentation, or make sure we get you answers afterwards. And Nancy, one that came in, you just answered about the difference between RCM and FMEA. And I don't know if there's further definition you want to include, but one person is also asking, in their organization that isn't embracing RCM yet, what's the right time to shift from FMEA only to a broader RCM perspective? Any thoughts?
Okay. So from my perspective, here's my take on just doing FMEA. I mean, obviously, it can be valuable. Just the exercise of just writing functions can be hugely valuable for the reasons, as I pointed out in this presentation. But my mentor, John Mowbray, when I asked him about that, I said, why would someone do FMEA and not finish with criticality and step 6 and 7, which is identifying proactive maintenance and intervals and default strategies? And the way he explained it is that, in his opinion, FMEA is just a bite out of the middle, because now you've got this, this document. If you do it properly, you've got this great document that's like a technical failure history of your equipment, and now you can use it to make very powerful decisions. So in my technical opinion, I don't see why you wouldn't just finish with criticality and proactive maintenance and default strategies, because that's where we make decisions on how to make sure we get those functions from our equipment that we identified.
Very good. And related question is, why do you think more organizations don't have an RCM program? What are some of the barriers you've seen, Nancy, to adoption of RCM?
Oh, I love this question. Thank you for this question. Okay, in my opinion, it's because I think to a very large degree, if we had another poll, I would love to do this poll. I think that RCM gets a bad rap. I think most people have heard negative things about reliability-centered maintenance, but I know in nearly all cases it has to be because RCM wasn't done properly. I mean, if you don't write, let's just take functions and failure modes, because that's what we talked about today. If you're on the left-hand side writing generic functions, you end up writing functions for pumps and impellers and nuts and bolts and resistors if you don't know how to do it properly. So you get into analysis paralysis with functions, and then you get so deep in detail that you kind of lose, you can't see the forest through the trees. And the same thing with failure modes. If you go into way too much detail and you write every single failure mode you can think of, or if you write failure modes too generically, you either end up with very generic results, or you never even get to the results because you've got hundreds of failure modes you're trying to think about. RCM gives us 4 criteria for what failure modes go into an analysis. Those that have happened before, those that have not happened but are real possibilities, those that are unlikely to happen but have severe consequences, and those that are currently being predicted or prevented in our current maintenance program. But then you need someone experienced to help you write in the right amount of detail and at the right level. So if you do that, you know, the compressor that we did the primary function for, that, like I said, that's a real world analysis. That analysis had about 160 failure modes. And with a live team, we did that in 9 working days. So one could say, wow, you know, we don't have 2 weeks to have, you know, 7 equipment experts spend in a room together. But we did that analysis because that compressor was chronically failing and costing tens of thousands of dollars a day when it was down. So again, I would ask the rhetorical question, it might be expensive to do it, but it's all relative, because wait till you get the bill for not doing it. So that's why I think RCM is not done more often. The other thing is, you know, with advancing technology, I think that a lot of organizations think if they throw a lot of money at high-tech condition monitoring equipment, then they don't have to do anything else. We definitely need the monitoring equipment, but we have to know what failure modes we're managing and how we're going to use that equipment properly.
Excellent. And a related question that another listener asked is, if you're ready to embrace this, Nancy, what's the first step you need to take?
Okay, the absolute first step is absolutely make sure that your team that's going to be doing RCM is properly trained, because reliability-centered maintenance has its own language. So if your team doesn't have, and I'm just talking about like an introductory course, you know, a couple of days just to learn the language, you may as well conduct the analysis in Greek, for example, you know, because within reliability-centered maintenance, we talk about like potential failure conditions and P2F intervals, and MTB, mean time between failure, and all different terms that we use in the analysis. So it's very important that they're trained. That, and have a trained facilitator, and you know, definitely have someone help you with your first couple of analyses to make sure that you're doing it right and get up to speed so that you're on your own. But don't skimp in the beginning and think you can just do it by like reading a book or taking one introductory course. That would be my most honest recommendation and advice.
Excellent. One point of clarification, Nancy, in one of your later slides, you refer to criticality. Does that mean that assets criticality toward keeping production running, or is that the consequence of the asset's failure? Can you just give us a little clarity on that? On
Yes. In
criticality?
the context of reliability-centered maintenance, when we assess consequences, we assess the consequence of each individual failure mode in our analysis. So we would identify if a failure mode has safety, environmental, operational, or non-operational consequences. Some organizations choose to quantify it by doing like assigning a risk priority number or other formal criticality analyses. And sometimes there are some individual failure modes that require a formal criticality analysis, but for the most part, in my experience, it suffices to identify safety, environmental, operational, and non-operational.
Okay. And one of our listeners is asking, perhaps you've heard the term an RCM blitz or light RCM. Is that something that you endorse or encourage?
So generally speaking, I know of RCM Blitz, but honestly, I'm not an RCM Blitz expert. So I will just say, generally speaking, if an organization wants to do reliability-centered maintenance, then it should be done in accordance with SAE JA 1011 and SAE JA 1012. JA 1011 is a very short document. It's like 9 pages, and it outlines what an RCM process must include to be called RCM, and that is the 7 steps that I outlined today. Now, that having been said, there are streamlined or shortened versions of RCM. You may have heard of, for example, PMO, Preventive Maintenance Optimization. And in an analysis like that, generally speaking, what an organization does is they take their current proactive maintenance plan and they reverse engineer their current tasks into failure modes. So they figure out if they should still do that task, maybe do it at a different interval, maybe do a different task, or maybe eliminate it from their current maintenance. And I'm okay with that as long as an organization accepts upfront that they're only dealing with the failure modes that are managed by those tasks. There are failure modes that you won't be analyzing. So really, it's just about what you want out of the analysis. You can relatively quickly optimize the maintenance that you currently have. But if you do full-blown reliability-centered maintenance, you will end up with an optimized maintenance program because in the context of RCM, we only identify a maintenance task if it's technically the right thing to do and if it's worth it, meaning it's less expensive to do the maintenance than to run it to failure.
Gotcha. Okay, I think we have time for one more question that's somewhat related. A listener is asking, where do you store all this data or manage the process of RCM to record results? And a related question is, do you recommend integrating it into your maintenance planning and execution system, your CMMS, or keeping it separate?
Okay, so number one, I absolutely recommend you use some sort of RCM software. I myself personally, very early on in my career, tried to use Excel, just an Excel spreadsheet, and it's just not worth it. So you definitely need some sort of an RCM database to hold the information. Now, as far as if you want it to hook up to your CMMS, I think that best case scenario, it would be wonderful to have that, but I would much rather see an organization spend their time and resources doing analyses the right way and then just manually taking the results and feeding that into their CMMS. And once they're up and running and they know what they're doing with RCM, then maybe integrate it. So it doesn't need to be integrated right off the bat. I think a lot of times, see, we don't want to get shiny object syndrome when it comes to RCM. John Mowbray taught me that RCM is thoughtware, not software. So the software merely supports and houses the information. The software does not make any decisions for the working group. Even if the software, like if you add in different variables and it might do some calculations for you, you still have equipment experts who have to provide the information that goes into that. So I would rather listeners today think about RCM as thoughtware and not software.
Excellent. All right, thank you. That's a new term to me. Well, we're out of time today. Thank you all. Thank you so much, Nancy, and thank you to our listeners. Gosh, but there's lots more questions. We promise we will get you answers. And we don't want the dialogue to end here. Nancy is going to be one of our speakers at a conference we have coming up in a few months, our Accelerate conference. Nancy, if you want to advance a slide, in November in Florida. This is a great opportunity to hear other passionate and knowledgeable speakers such as Nancy. There's thought leadership tracks, best practices, product training, see the latest and greatest in both thoughtware and software and hardware. So that's my new term for the day. And that's in Southwest Florida in November. We hope you'll join us there. We're also going to be posting a recording, Nancy, if you advance a slide, of today's session on the Excelix website. And when we end the webinar, there's going to be a brief survey. And please take a moment, let us know how we did. Let us know what other topics are on your mind so we can get people such as Nancy to address them and share input. So thank you to everybody. Thank you, Nancy, for putting this together. It's clearly something you're passionate about. I'm excited about it as well. And thanks to all our listeners today for your participation. And on behalf of Fluke and the Excelix team and Force Inc., thanks and have a great day. We'll see you all the next time.
Thank you. Thank you, everyone.